122. Let's talk about extra groups and extensions. So we have recall the definition of extension in the last exercise. So let's directly going to prove some exercises. So firstly, lemma. Prove that if x star 1 a b equals 0, then every extension of a by b is split. So we're still following Weibel's book. Solution. So let's first recall extension of a by b means extension of a. So we got some extension of a in the sense that quotient by b gives you back a. So if we have the condition x star 1 is 0, then extension is split, is a trivial extension. So let's just start with arbitrary extension. Let's call this c, and then just apply this extra functor. We have so we're applying the functor home. So this contravariant functor. Applying this, and we got home a extension of a by b. Yes. And then home a e home b a extra 1 a, but this is not what we want. So let me modify. I'm going to let me apply this. So I'm going to apply this covariant functor, and then home a b home a e home a extra 1 a b. But if we are supposing this is 0, then here we got this identity element. Just by the definition of category, so the identity morphism always exists. So there is this identity element with this home set. If this is the category of our module, that this is group, and this is identity element of this group. And then there is some element. Let's call it beta, such that this is mapped there. So recall what is this map. So if we call this pi, call this j, J, then this is called the I. This is the map A to E, A to A. Which means composition by pi. Which means there exists a map, it's called beta, such that beta compose pi's identity. This is saying that it's split. Okay. Remark. We see that the class, let's call this partial map. So this is mapped partial identity. In this case, partial identity is 0. In general, when we don't know this extra one is trivial group, then the image of identity, it might not be 0. In this case, the class corresponding to this identity, partial identity, in extra one is an obstruction. This is a word a little weak, but it's very commonly used, obstruction. Its meaning is literally meaning it stops something, right? It's the obstruction. It's the obstruction to this equivalent class is C to split. Because as you saw, when this is 0, then it splits. But when it's not 0, it's not necessarily split. And so the non-zero or the non-vanishing of extra one, or it's telling you that there are some non-splitting or just be safe and specific as we described here. The obstruction of C being split is this image under the differentiation partial of the identity of A. So a natural question is that surely the definition of extra one A, B only depends on A and B, right? Same doesn't depend on this equivalence. This surely that sequence C. But let me write down C is split if and only if identity of A lifts to home EX if and only if. So in our case, say E. Our extension is denoted E. If and only if. The class of extension 1 AB vanishes. And furthermore, equivalent extensions have the same obstruction. By naturality of partial. So the obstruction only depends on the equivalence classes So maybe let me change the notation to avoid confusing. So let me just, so at this moment we haven't really gave a bijection between x01 group and the equivalence class of extension. So this partial of identity A is elemented as x01 group, while this C is an extension. So let's give notation. I mean, you could avoid giving this notation, just use partial identity A. But to just say more clearly, this partial identity A is related with C. Let me change the notation to this. It only depends on the equivalence class of C. Okay, so again, back here. The question is saying that this x01 groups, okay, depends on A and B, while why this image of identity A is related with a specific C? Because, so superficially, because we got this line exact sequence coming from the short exact sequence, right? In other words, how do you got your map partial? Your map partial comes from a given short exact sequence. And so it somehow relies or depends on your given C. And here what we are saying is that actually it depends only on the equivalence class of C, not on that specific one. Okay, you could think of this as a sub-exercise. Well, the idea is that, as hint given here, natural additive partials. Partial is actually a delta functor, and you could imagine that if you start with a C, let's say a extension of A by B, extension of A by B, so this is E A, and then you have another one, C prime. So suppose the they're equivalent by definition, this is what it means. But then by the definition of delta functor, this partial actually satisfies the condition and translate to line exact sequence, still make commutative diagram commutative. So what you've got is you've got so sorry. So yeah, we apply that home A, B, home AE, home AA, next term 1 AB, etc. Right, and then what you got is you always have this commutative diagram, and this is just a functor given by the home. So here, what's the, we got A to B, and then composition with this map, which is identity. So this is actually just A to B. And here, let's call this F. Actually, you got A to E, and compose with F. Right, got a map to A to E again. And here again, home A to A. And then here we got your partial. This partial will tell you that. And this partial, there should be, again, a map. Like this. And so you say that so you got your identity A here, and you got identity A here. This is mapped to, let's say, C, obstruction C. This is mapped to obstruction C prime. And then you will see that this gives you isomorphism. Because this is isomorphism. So before I proceed, let me firstly quickly recall the definition of delta functor. So covariant, homological, respectively, homological, delta functor, twin, two category, A and B, is a collection of additive functors that's denoted by Tn, respectively. I put it on the upper index to know the cohomological functors. So n is bigger or equal than 0. together with morphisms, delta n, tnc to tn minus 1a, respectively delta upper n, t upper c to t upper n plus 1a. And this is defined for a given short exact sequence. Short exact sequence A to B to C. So our case above, this is extra I A gamma slash apply on this short exact sequence, extension short exact sequence. Here we make the convention that Tn when n is negative, zero factor, zero additive factor. Furthermore, two conditions are required to experiment. For each short exact sequence as above, there is a long exact sequence. Respectively, cohomological one increases the index. In particular, T lower zero is right exact, T upper zero is left exact. In our case, this T upper zero is whole A gamma flash, is left exact. Second extra, this is the one I used. So for each morphism of short exact sequence from first one to the second, the delta give a commutative diagram. respectively. Remarks and also examples. Homology gives a homological data factor. Each lower index or lower start from chain complexes to A, respectively. Cohomology gives a cohomological factor, data factor from cochain complexes to category A. Sub-exercise. Let S be the category of short exact sequences. Zero to A, B, C, 0, A. Show that delta I is a natural transformation from the factors sending short exact sequence to Ti of C to the factors sending short exact sequence to Ti minus 1 of A. Right. So this is more or less this one, the second extra. And so, in particular, for that category, it sends a morphism. Morphism of short exact sequence, which will be a morphism of complex, making the diagram commutative, to Ti say Ti say prime and then Ti minus 1a, Ti minus 1a prime, right? Here is your delta I. Make a diagram commutes. And in particular, in our case here, coming back to our case, so we got this C to C prime. right? And then makes this diagram commutative. And then the category of shortly sequences. This is isomorphism. And so the commutative of this diagram is just telling you that. So this is identity. It's just telling you that under the isomorphism of the group, this is mapped to this. Right. And so up to isomorphism, this obstruction of extension is independent of the choice of particular extension up to equivalent classes. So what I'm thinking is, I'm thinking how do I justify here is the isomorphism of this group. This is because I think we could either use something like phi lemma. You have commutative, you have morphism of complexes, and then if all the vertical ones are just isomorphisms, then the one in the middle should be So if you really want to recall how is this morphism constructed, then should be obvious. This is isomorphism because it is induced from the vertical maps as on the first arrow. On the first column is identity, second is isomorphism, third is identity. So each column should be isomorphic. If you just recall the definition, so this would be just the right derived functor of the left exact functor of we're applying this covariant functor on this object B, so you take projective resolution. So you take a resolution for B. And they apply this functor. Here this map is given by identity, right? So resolution of B is translated to is mapped to resolution of B, just the same resolution. I mean, in other words, here we are just using this map from B to B, induce a map from external one, A of B to, or in other words, external one of A to B. So let me put another remark here. Assume category A has enough projectives, then for any right exact sequence, for any right exact functor say f from category A to category B, the derived functor form universal delta functor. So what is universal delta functor? Firstly, let me recall. So universal delta functor means that for any that there is some universal property, which means when they coincide on the first, there is natural transformation of delta factors. There is this unique morphism extends this. So let me write down more precisely. So morphism of delta functors is a system of natural transformations. So recall delta functor consists of a collection of additive functors, and the morphism of it is defined to be a collection of natural transformations for each fixed n. And after we define morphism, we see that a delta functor is universal if for any given delta functor S with natural transformation. S0 to T0. So you think of homological think of homology as a delta functor. This is telling you that if you have the first homology group and the second, if you have morphism between the first homology group, then it extends uniquely to the morphism between all the homology groups, if it is universal at the beginning. Yeah, cohomological delta functor T is universal if given S F0, there is this unique morphism of delta functors extending this F0. As an example, homology from the chain complexes to the category is a universal delta functor and also cohomology version. Let me add some more remarks. Firstly, the objects. So RIF, the left derived functor of f. So f is from A to B. A well-defined up to natural isomorphism. That is, if you have Q to A is a second projective resolution, then there is there is a canonical isomorphism. So by definition, this RIF, lefty right functor of f, is defined to be evaluated on given object A. This is defined to be homology, ith homology of f of P, where P is projective resolution of A. And this remark is telling you that if you have another different projective resolution, then it always give you isomorphism, canonical isomorphism. Second remark, if you have any map, it's kind of talking about the functoriality of this lefty right functor. If you have a map there is a natural map, call it LIFF, for each I. Let's say the idea of the proof is, suppose you have projective resolution, by so-called comparison theorem. Which let me recall here. Let statement of the comparison theorem, let this P to M be projective resolution. And let's give it a map from M to N. So M and N are objects of category A. Then for every resolution of N, let's call it eta, there is chain map from the first resolution to the second, lifting f prime. This is very like the picture, the realization is very similar as how we define universal delta functor, right? But here it's only in the level of a resolution, the level of maps of modules. In the sense that, so let me first draw the picture. Projective resolution 1, given f prime at the beginning, projective resolution of n, and then it's claimed that this morphism, making the diagram commutes. And this map is unique up to chain homotopy equivalence. This is, recall this comparison theorem. So let's back here. Suppose you have a given map in the category A prime to A, and then take respectively two projective resolutions. And because you already have this F from A prime to A, and then by this comparison theorem, this could be lived to a map between projective resolutions. Right. Let's call it F tilde. Unique up to homotopy equivalence. Unique up to chain homotopy equivalence. And then because you got this map on the project resolution, this further gives you a map on the homology with it, which is right. Let's call this F tilde star. And by the theorem, any other lift with chain homotopic to F tilde. And so this is independent of. So the chain homotopy is exactly telling you that their homology groups are isomorphic. Give the same homology groups. So this is telling you that this F tilde star is independent of choice of the lifting. And hence we have defined such a map, well-defined map. Let's just define this to be our HIFF. Okay. So let's give the proof. I could just call this exercise 2. Let's back to our situation again. So this is exactly in our case. So this, we're talking about this extra is just the right derived functor of this left exact functor f. This is our f. This is Ri of f. Applying on B, and B we should take injective resolution. And we take two injective resolutions. Sorry, we take injective resolutions on B, and here we give you a map from B to B, and this will be lift to up to homotopy equivalence, a unique lifting of their injective resolutions, which means after you compute the extra groups, it should be the same. And obviously here we are giving B to B by identity, and so actually up to homotopy equivalence, you could just think of it the identity lifting, and which means you could even think of this as just identity, or just call it isomorphism, because we're talking about homotopy. We're talking about a lifting up unique up to homotopy equivalence. You could take something other than identity lifting, but finally they will give you the same homotopy groups, which means their homotopy groups must be isomorphism. Okay, this kind of coming back and explains this sub-exercise also. So actually we have proved this. Let's put this as exercise 2. So exercise 1, exercise 2, let's call this 3, because we first explained how is this morphism constructed back into the very definition of left-right functors, which is defined to firstly take a resolution and then compute its homology groups or cohomology groups. And we have proved the lemma that thanks to this comparison theorem, the different lifting doesn't influence the homotopy of that projective resolution. After you apply that left or right exact functor, and so a map between the objects gives you a map between the homology of the right or left exact functor applying on projective or injective resolution of that object.